So I'm going to get rolling. Basically, this is a follow-up to the previous lecture. I'm going to try to not make it I tried to not make it redundant. This is actually just the entire fast mapping workflow from just start to finish. So for those of you who are not quite sure what fast mapping is, it's the newest extension to the X-Nav. And what I'm going to show you here is how we further the discussion on minimizing errors. So imagine a world where a surgeon has access to everyone that they want to work with without having to have them be local. This isn't the magic act I've been pulling off for the past couple of years because I moved out of state. And the amazing thing about a completely digital workflow is that the surgeons can actually send me an entire data pack and have me process it so that the first time I actually meet the patient, they're probably sedated because they're already in the chair for surgery. And just to make it even more interesting is that because there's so few post-op issues involving things fracturing or so on and so forth, I only see the patient maybe 3 times from start to finish. So I might not get the whole patient's story and how they wound up in the chair. However, I get to experience their great outcome with them. So a lot of feedback I've been getting from surgeons I work with is, you have no idea how you changed this patient's life. And he's like, you are absolutely correct, because all I know is this cheerful person sitting in front of me. So what's going on is that with the ICAM workflow that I just went over, is a 2-visit immediate loading series. The biggest kicker in here is that we still need fiducial markers, whether it's teeth, fixed artificial markers, or none. Problem with teeth is that it requires a minimum 2 to 3 teeth, minimal mobility, and can get in the way of surgery. With fixed artificial markers, we still have to rescan the patient before starting surgery. The markers might move and create issues, and it may interfere with flat reflection. I've had this happen where the surgeon thought they were being crafty by just pushing the markers back in, and there was me sitting in the chair going, why is none of this data coming back together? And lastly, there's none, where we have to use a denture wash and basically still need to use goop of some kind in order to translate the jaw position back in with the floating scan bodies. So the issues that come up with the ICAM workflow involve the surgical planning and mostly in the soft tissue scan. Because what it results in is new error points that we didn't have before, which is where if the data doesn't merge perfectly, suddenly we're adjusting occlusion, we're trying to figure out why everything looks a little bit off. So when fast mapping came out, I said, okay, how is this going to make things different or make it better? And additionally, it meant that I would have to work with a surgeon who knew how to use the X-Nav already, because that's a whole other modicum of doing surgery. So when we look at the FastMap navigated photogrammetry workflow, one thing that it does differently that the ICAM cannot do is actually merge the data sets for you so that you don't have to rely on the lab to do it, and you don't have to question whether or not the data is sufficient. I'm going to show you a couple of scenarios where things might still go sideways. However, with the FastMap scan body and that workflow, the software also tries to clean up your data for you. So with the FastMap flow, overall, it still looks pretty much the same. Not much has changed. What has changed is what goes on in the surgical step. You have to attach appendages and actually use the exocad appropriately. But what you'll see is in digital conversion, we're down to 1 step, which is just picking up the FastMap scan itself. And after that, everything goes back to printing and finishing. So why integrate navigated surgery? How many of you have full faith in freehand surgery 100% of the time? Like every single time, the implant goes exactly where you can imagine it wanting to go. So there are some surgeons out there where they need a little help because for whatever reason, It might be the surgical setup, it might be they're new to an office, or they want better control. What you're going to find over paper after paper, meta-analysis after systematic review, in every single journal you can ever find in implant dentistry, they all more or less say the same thing. Guided surgery is generally more accurate than freehand, and when done correctly, you have a deviation of maybe 1 to 2 millimeters at most from the planned position. Clarity of the CBCT seriously matters when it comes to planning a dynamic surgery. And lastly, most of all, it works. So for some surgeons, it helps them do a better job at being a surgeon. And for those who are freehanding well, I'm not here to tell you that you need to convert, because obviously you're having a great time. In terms of the FastMap workflow, I'm going to walk you through how everything can go from start to finish. We're going to work through one patient together. This is with a local surgeon who is the only one who ever met the patient before, Dr. Epstein, Matt Epstein. And then the digital designer I worked with on this case is a remote lab technician who works from home, Matt Kim. And the data micromanager, or me, the on-demand pros, is me, not Matt, Yeung. So the in-office equipment that's required to pull off a case like this is an intraoral scanner, CBCT, X-Nav with NXT extension, FastMap scan bodies, 1 per MUA, a printer ecosystem, and PVS gun and Blue Moose, just in case I need a plan B. Because I don't know about everyone in this room, I always have plans B and C ready to roll, just in case anything gets weird. In terms of additional needs, is to make sure that the technician is ready and waiting for the data when it arrives. So what I'll do is schedule the surgery and then ask the technician to clear about an hour of their own time just to sit and wait for me to send them data. And that's how I can get the 20-minute conversion time. So it starts off with the surgeon sending me a CBCT and also a DTX plan of where he thinks more or less implants can go. We hash it out, stick on the MUAs, determine what parts we need to order. And usually I'll do the same on my end just to see if we have consensus, and usually we do. And with this, we can actually move forward with surgery. So with X-Nav, you can export it from DTX and bring it into the hardware. So the plan will go 1-to-1. Pre-op planning concerns involving a self-stitching system, as you can see in the slides that they're flipping through, is that there was a ton of scatter in the CBCT. What is the problem with having a ton of scatter from a prosthetic standpoint? I can't tell where this patient's teeth are. So if I have an STL or a diagnostic scan or stone models even of this patient, I can't relate it to that scan that well. And so we tried to clean up the data a little bit, but we already knew from the start that because this patient had so many pre-existing crowns, that we might have to do some kind of occlusal adjustment as part of finishing. Because with all that scatter, there's going to be an issue with automated soft tissue merging, and secondarily, the issues that we are considering with the AP spread and prosthetic modifications needed to compensate for the AP spread, if that happened. So compensatory strategies I thought of before the patient's even in the chair and before I even met the patient was, one, we need to prepare for a soft tissue wash impression just in case. Prepare for occlusal adjustment, so make sure we have all the armamentarium for that. And then from there, we can modify the design for a shortened dental arch so we minimize the cantilevers. Because for any kind of printed restoration, we need to plan it out as though we're doing a full arch zirconia, meaning that we can have 0 cantilevers because we're going to have a risk of fracture right where the cantilever is. So just for fun, I did a design challenge with the technician just to see where things should go, because this is how the patient started. I'm not sure why the occlusion looks like this. I have nothing to do with this pre-op. Designer did one version and I did one version, and you'll see that they're fairly similar to each other. Biggest difference was I was trying to decide whether or not we wanted to reposition the patient as more of a skeletal class 1, or we wanted to go edge to edge, and because of the patient's pre-op, we couldn't decide which one. From there, we can move forward with the workflow. So first, the surgeon will have to mount the tracker, then calibrate the X mark, do the guided surgery, mount the scan bodies, do the scan, and then export the file. And my role in all of this is literally right here at the end. So the entire time, I'm just kind of watching the surgeon, overhearing conversations, seeing if there are any modifications I would have to account for during the design process. Technically, I don't have to be at this surgery because all the equipment's already at the office. And that's it for now. I'm just kidding. So I'm going to walk you through the case. So this is the patient sedated. Here's the pre-op. So you can see the FPD was actually as distorted as it was reflected in the digital design. Here's the entire setup where we're ready to attach everything. Step one is to mount the tracker. And this video could have easily been about 10 minutes, but since the surgeon has been using the X-Nav for every single case he's done in the past year, this is a very fast process. So once he identified where he needed to place the anchorage pins, goes ahead and mounts everything onto that. So there are the 2 pins in place. And part 3, that's what it looks like when everything's ready to go. Next step is to calibrate the X mark. So what you're seeing Matt do here is to calibrate everything under the scanner that's overhead. That's why there's the blue light being cast. If you're wondering how I'm taking this video while I'm taking pictures in the background, it's because I'm using a tripod. But basically what's going on is that he's calibrating with his pad each time he places another implant. So this is what calibration would more or less look like. Basically, the idea is that both of these pads have to be visible under the scanner before proceeding. And when in doubt, he'll calibrate again. So if you were to watch his entire surgery from start to finish, he probably calibrates about 15 times to place 4 implants because he was being extra careful. So after that, the implants are in, and we place MUAs. This is a newer design, so we don't have to worry about osseous impingement anymore. And the reason why I took this picture before we sutured up is because guess what? It's easier to scan before you suture. And also, you can visually make sure that every scan body is seated completely. Because if you had sutured first and then seated the scan bodies, you're completely relying on either taking PAs or tactile sensation to ensure that the scan body is completely seated. So I actually prefer to do all my photogrammetry scans before suturing. So replacing scan bodies, this is occurring in real time. It's really quick. What you'll see is that these are about 1.5 inches tall, maybe 1 inch tall, but it doesn't get in the way of access. So we place all the scan bodies, then we start the scan. And this video is occurring in real time. What you'll see is that the scan software is actually quite smart in that it will actually keep going and tell you when it's finally done. But as soon as you see the little green checks, that means there's enough data for it to capture, and what it's doing is basically capturing the reflection of each scan body relative to each other. This entire scan process, when done efficiently, is about 1 minute. The reason why the scan is taking a little longer than expected is because they had to retract the cheek in order to catch the last one. Now the next step is that we have white caps placed, and I tell the surgeon to go ahead and start suturing. Meanwhile, I'm exporting the data, or anyone can export the data from the X-Nav. And it just creates a nice little neat file with the soft tissue and the scan bodies merged back in with a diagnostic scan that was imported into the CBCT. And after that, I sent the data off for processing. I took an extra soft tissue transfer just because I wasn't quite sure if the data would actually match up properly. So after I sent the initial batch of data off to the lab, I made an extra denture wash just in case. And here I can actually show you what the difference in output was, because as we all saw, With a CBCT, it had a ton of scatter in it, and tried as we might to match the cleaned up scan data, or CBCT, to the diagnostic scan, we already knew there was going to be some degree of error. And so what you're seeing here is a deviation of probably about 1 millimeter. How long does it take to adjust 1 millimeter of acrylic in the mouse if your occlusion is off? It could be really, really fast or really, really slow, right? But usually less than 5 minutes. So because I saw this data mesh, I was like, all right, you know what? Let's just proceed. So from there, I checked the design one more time before we send it to print. What you're seeing here is an overlay of the denture setup that we had created initially. That's the reason why it looks like it has little wings, merged with, or overlaying the actual restoration that will go home with the patient. So the brighter green is actually the restoration that we're going to print. The darker green is the denture wax-up that we merged. So at this point, again, I'm checking for contours, tissue relief, screw channels, sufficient bulk where I want it, cantilevers, and so on and so forth. And this is the file that is output from that design. So I always do one more check before I actually send it off to print, just to make sure that the file merge went well. I can go ahead and nest it in Rayware, which is the software for sprint ray units. You can see that my lab tech likes sending me passive-aggressive messages in jest. And from there, this is in real time. The software will set up the print for you, so all you have to do is make sure that the supports are exactly where you want them to be before sending it off. So this process takes about 1 minute. And if you don't have an internet connection, that's going to be a problem. But as long as you have Wi-Fi, you're fine. Add your supports. Make sure that they aren't near any of the screw access holes, because if you have a support near a screw access hole, what will happen is that you'll print an entire channel that goes through where you don't want it to be. And from there, we send it off to print. At this point, I use a nanocure, which allows a slightly better outcome from what I've seen, in that it has a better cure time and a better overall degree of conversion, because I have way fewer complications ever since changing my curing unit. But this is the cleaning process. Just a spritz of alcohol. And after curing, I'll glaze. This is just maybe 5 minutes of glazing. And insert. So what do we see here? What we're seeing is exactly what we saw in the design, where the patient actually was finished in a slightly opened occlusion. Is this a real problem? If we send the patient home like that, it can be, right? But if we adjust it, it's only going to take about 5 minutes. So in terms of the finishing protocol, basically we do the same thing again, where we start with a post-surgical scan. So this is the nice thing about X-Nav, is that you don't actually need to have a mount on the patient every time you want to do a scan. You can actually scan bodies independently. It just means that you have to do an additional tissue scan in order to relate the restoration back. And from there, you can move on to the final restoration. It can be done in whichever format you want. And when you're looking at the digital workflow in terms of how it adjusts data, is that they'll actually account for the initial scan and accept that probably most of them are accurate, and just change up the data so that for the ones that don't match 100%, they'll kind of finagle it in and move forward from there. So if you wanted to do something more tangible, you could move on to something called Guided Smile, which is a stackable guide system. And basically with the stackable guide system, what happens is that you will receive a printed restoration, or you can choose to print it yourself. But the entire surgery is guided with a metal frame, and each guide that goes on is yet another stack. So this video was provided by one of my local rep friends who followed an entire case from start to finish. And what you'll see is that with a metal frame guide, what happens is that it actually guides you every step of the way from osseous reduction to seating for the final. If you don't want to do a conventional conversion, from here you can still pivot to using either iCam or another full large scan system to reach your finish line. So thank you for joining me through this series. I tried to make this more succinct because I figured everyone wouldn't want to hear me for a solid hour and a half. So if you have any questions that's specific to this system, please go ahead and ask. That's why I also wanted to leave extra time for it, because this one is actually more curious for most people than iCam at this point.